appropriately. And I want to dedicate this talk to the memory of my advisor, mentor, and friend, Steven Weinberg, who very sadly passed away in the summer of 2021 at age 88. You can read more about Steven Weinberg in the obituary that appeared in Physics Today in 2021, and also a talk at the Texas APS meeting. And I'll be happy to send you the link to the talk and the Physics Today article if you write to me. So the story behind this talk started about 6.5 years ago, June 10th, 2016 to be precise. And I got a call out of the blue from Steve Weinberg, and he asked me, I have some questions about atomic clocks. After a brief moment of panic, I responded, sure, I'd be happy to talk to you about it. And he had many questions that he could summarize in a preprint that he had just prepared entitled Lindblad Decoherence in Atomic Clocks. The abstract of this preprint is, it says, it is shown how possible corrections to ordinary quantum mechanics described by the Lindblad equation might be detected by exploiting the great precision of atomic clocks. And I love the first sentence of his paper. In searching for an interpretation of quantum mechanics, we seem to be faced with nothing but bad choices. So Steve Weinberg had the idea, and he's been thinking about this for many years, about possible extensions of quantum mechanics, especially not being happy with the current interpretations of how quantum system interacts with the environment, the whole concept of a collapse of a wave function, etc. And he particularly wanted to know if there could be a real observable that would be a consequence of an extension of quantum mechanics. And what he said, in essence, is that if you have an atomic clock, there could be an environmentally induced shift in the frequency of the clock. But of course, if you only have one clock, then you don't know if that's the natural one predicted mechanics or the effect predicted by his extended theory. So instead, he said, what if we have a clock, or an atom rather, with 3 connected clock transitions? So depicted here in this figure, we have states A, ground state, an excited state B, and another excited state C. And a transition from A to B is denoted 1, from B to C is denoted 2, and A to C is denoted 3. And if each of those levels is shifted by a different amount, let's say, ignoring there's no shift of the ground state, but there would be a shift of state B and C, then in principle, perhaps if we add up the frequencies, 1 plus 2 does not exactly equal to 3. And that's the question that he posed. And so, as in Steve's paper, he worked out the theory. He couldn't make a prediction on to the size of this effect, but he pointed out that this would be one way to test it. And the question that he had for me is, was there an experimental system where this could be tested? Well, I looked quite a bit, and I couldn't find a way to do it. And I was very disappointed that I couldn't identify a real atom that had these 3 connected clock transitions. And I had to tell him I can't find one. Well, Steve said, let me ask someone else. So he contacted David Wineland, who he also knew, and asked Dave if he could identify such a system. And Dave thought about it for a while and came back to him and said that he also couldn't find one. Well, I have to say that made me feel a little better. But the upshot is that there was no obvious way to do this. And nevertheless, the paper did get published. It had some difficulties with referees, but in the end, it got published in Physical Review A. And Steve and I met many times afterwards, but never talked about this again. It somehow didn't really the paper didn't get noticed much in the atomic physics community. and we didn't discuss it any further. Well, after Steve passed away and I was working on the obituary, it gave me an opportunity to reread many of his older papers. In particular, I reread his 2016 paper and had some ideas since then got together with two friends, Jerry Gilbert, another former student of Steven Weinberg, and now a fellow of the Meitner Corporation, and Dima Butger from University of Mainz and also UC Berkeley. And together, we identified some recent results and with new ideas, and the upshot was that we came up with a way to do it. Well, the first thing was that we identified current limits set by experiments. We found two cases of both ion experiments, radium and calcium, singly ionized. The simplified Grotrian diagram for radium is shown here. Calcium has a very similar structure. The limits for the case of radium ion are about 30 megahertz in this 1 + 2 = 3 relationship. And for calcium, it's better, about 100 kilohertz. However, strictly speaking, these two ions don't satisfy the criteria of being 3 clock transitions. So there was a clock transition, but also dipole allowed transitions. So this kind of case would never be amenable to very high accuracy test. We went back and looked through the literature and thought about it more and came up with this system, ytterbium, neutral ytterbium atoms. And here's a simplified Grotrian diagram. Ground state singlet S0 and so on, other states. And we identified 3 connected clock transitions. Some of the states shown here with their energy levels in inverse centimeters and lifetimes are shown. The singlet S0 state is shown at energy 0. It's a stable state, it's the ground state. But you can identify the triplet P0 state which is the standard clock transition in atomic ytterbium is 22nd lifetime. And the J = 2 state has an estimated 1 minute lifetime. So that gives you 2 out of the 3 legs. And to complete the picture, we realized that we could drive a transition with 2 photons. So this is the schematic that we proposed. And the A to B is a green laser at 578 nanometers. That's one. A 2 is a transition, and this was only reported in 2018. So in 2016, it had not yet been done at 1695 nanometers. And then to complete the 3 legs, we propose a 2 photon transition at near 862 nanometers. This is one possible system. And put it on the archive, and it got published in 2022. And since then, we've been contacted by many groups, and there are experiments in progress. Overall, there's been very interested response by the community, and people have come up with other potential systems this could be tested. So I think we now just have to wait. In our acknowledgement, this is the best that we could say. We wanted to dedicate it to the memory of Steven Weinberg, but the editors wouldn't let us do that. So instead, we just said we are grateful to the late Steven Weinberg for discussions about this topic over several years, the memory of which inspired this work. And we like to think that this is perhaps the best tribute to his memory, because it's trying to complete something that he left unfinished in 2016. And I think he would be pleased. And he would be even more pleased if we find, or other people find, that 1 + 2 does not equal 3. Wouldn't that be something? All right, I want to move on to something else. And that is a different question about quantum mechanics, and one that unfortunately I did not get to discuss with Steven Weinberg. I regret that. I'm sure we would have had very interesting discussions about it, but it's something that's been on my mind for a while. And the question is, do atoms age? And what I mean by that, not, of course, they don't get gray hair, etc., and walk with a cane, but is there some measurable quantity that would change in time? In particular, if you had an atomic clock, could you see a time-dependent clock shift? Well, this has been discussed a lot, and in fact, searched for experimentally in atomic clocks. It goes by the topic of time variation of the fundamental constants, which has been the topic of a lot of discussion, but so far is a null result. Of course, one doesn't really have a control knob because you're looking at the evolution of a stable atom, and the time scale is the lifetime of the universe. So in fact, there's really not a good theory that would predict it. But nevertheless, these sort of searches are very interesting because if they find something, that would really be a revolution in physics. But what I mean here is something a little different. And in particular, what I mean is the concept of an atom having an age. Well, when we think about what does aging mean, it means there's a birth and a evolution time and finally death. And this happens, in fact, for radioactive atoms that we can create artificially. For example, we can create a radioactive atom in a nuclear reactor, as shown here. And it has some typical half-life, T1/2, and then it undergoes decay, shown here in this picture as alpha decay, and it changes to a different element, and we can call that death. Well, the question is there something changing in the nucleus, some unknown parameter, that this would be outside of standard quantum mechanics, but after all, we don't really have a good theory for the structure of the nucleus. It's a non-perturbative QCD, one of the hardest problems still to solve. And so this is not an unreasonable thing to ask. But even though I've thought about this for a while, I didn't dare write a paper about it because it would seem too crazy. But Idima Butker introduced me to Surjit Rajendran, and then through him to David Kaplan, two outstanding theorists from Johns Hopkins. And as we talked about this more, it turned out that they actually have a theory that would incorporate this kind of effect, which we called atom aging. So we worked on this together and published a paper. The paper was unusual in several respects. One of them, it surprised me how easily it got published compared with our 1, 2, 3 paper. This one just flew through and the referees were enthusiastic. The other thing that surprised me is that the editors let us keep the title, which I like very much. Do atoms age? ? The answer is we don't know yet, but there can be experimental tests done, and there are many possible systems. In case of trapped ion clocks, one interesting case is lutetium-177, which is a beta emitter. It has a half-life of almost 1 week and peak energy of about 500 keV energy. Another candidate would be a radium ion, radium-223, with a half-life of 11.4 days, an alpha emitter. And another also, we could consider radium-224 and radium-225. These are other intermediate life, unlike radium-226, which has 1,000 years lifetime. These are measured in days to weeks. In the case of neutral atom clocks, which would be outside the theory of Rajendran and Kaplan, but nevertheless one could look for a candidate that's very interesting is strontium-89, because strontium is currently the best neutral atom clock, and the Junyi group at Jilla has pioneered that and shown extraordinary accuracy of the strontium clock in an optical lattice. And strontium-89 has a half-life of 50 days roughly and is a beta emitter, so could also be an interesting candidate for this test, because you could really run these clocks for timescales that are long compared with the half-life. And so now you have an knob. You're not comparing with the lifetime of the universe, but rather with a lifetime that's measured in days or weeks. So, you know, I think we will learn. There will be experimental tests that'll search for this effect. And it's not at all a sure thing. This is one of those things that is simply untested experimentally. And so it's interesting whenever you can find a new test of quantum mechanics that hasn't been done yet. And so this is one of those cases, and it's definitely worth looking for. What I would say in addition is that if this is found, not only would this require reformulation of quantum mechanics, but it could actually be useful. It would be allow one to do what I would call nuclear forensics, because you could imagine doing radioactive dating with a single isotope. For example, if you measured cesium-137 or strontium-90 in the atmosphere, those are fission products, and you don't have anything to compare with. So it's not like radioactive dating that you're familiar with, carbon-12 versus carbon-14. Here, you are just looking at cesium-137 or strontium-90, but if you could tell by their clock frequency what their age is, then you would be able to determine when they were emitted, when they were formed. And so we'd call that nuclear forensics. But that's very speculative. I think one first has to search for this effect. Okay, in the time that remains, I would like to mention a few recent results in my group that I don't have time to talk about in detail, but I'll just mention them briefly. First of all, we've been continuing to work on efficient cooling methods of atoms, and relying on earlier work on one-way wall Maxwell-Diemann cooling. We've now realized how to apply this to high angular momentum systems, such as atoms with a very large magnetic moment in their ground state, such as chromium, erbium, or dysprosium. And what we show theoretically and through numerical simulations is that these high angular momentum systems are very amenable to efficient cooling. And this could be an alternative route to evaporative cooling of atoms. And they're resulting in much larger numbers of quantum degenerate gases. We've also done work on thermometry of microparticles in real time using short-time Brownian motion. These are published results, and this could be useful for measuring or study of turbulence of heterogeneous nucleation. And very recent and unpublished results is ultra-sensitive sound detection, also based on our short-time Brownian motion work. I'll say a few more words about that. So if you think about measuring the acoustic velocity of sound, where you have small particles that are entrained in air, could be also in a liquid, but we are considering air, then the microsphere velocity follows the acoustic velocity, as you can see from this little animation. This builds on our earlier work on short-time Brownian motion. This field was really predicted by Einstein in 1907, where he said that at short time scale, sufficiently short time, the irregular random Brownian motion becomes predictable and regular. And that short time Brownian motion was first observed in our group in 2010 in air, and then in 2014 in liquid. And all those experiments were done in thermal equilibrium. Well, now we have used the same system to develop a quantum limited acoustic detector. And the general idea is that if you have a fast sound event, a fast acoustic signal, then if it occurs during the time scale when Brownian motion is not random, then we actually know what our transducer is doing. So in a way, it's information-driven detection. And because we are not detecting against a noise background, we can be quantum limited. And this will allow us to have sensitivity that far exceeds any detector or microphone. So this was the idea. And we still unpublished results, but very encouraging. We invested quite a bit in state-of-the-art sound detection. I generically call it a microphone, but it's a very expensive microphone, the best money can buy. And we compared that with our trapped optical microsphere, and we created different sound sources. In the first case, we just made a 40 kilohertz signal, a buzzer, and we compared the measurement of the microphone and the microsphere, and you see that they are in very good agreement with each other. So those detectors track each other extremely well. But then we changed the sound source to a fast pulse source, which is due to a pulse laser, nanosecond laser on an aluminum target, causing laser ablation, and that shockwave. And we can detect that, and you can see here the blue is our microsphere with the highest bandwidth, and the black is the microphone, and the orange is the microsphere, but with limited bandwidth. We just impose post detection. And you can see that we surpass the state-of-the-art microphone or preliminary measurements. There's much room for improvement in our results. We can do a lot of things to improve the signal to noise. So I would say at this point, we have the world's most sensitive acoustic detector. And the question is, what would be used for? So two interesting potential applications. One of them is to pinpoint the stopping of protons during proton cancer therapy. In the case of cancer therapy, one accelerates protons to an energy of about 200 MeV, and then they penetrate into the body until they reach a certain energy, a certain distance where they deposit most of their energy. That is called the Bragg peak, and it's a very short distance. The problem is that there's no good way of imaging the stopping of the protons and making sure that that overlaps with the location of the tumor in the body that you want to eradicate. We are looking into the possibility of using our fast detection, of course, not with a tweezer, but applied to a more real-life situation, where we could triangulate by the shockwave arrival time and triangulate back to determine the stopping point of the protons in the body. Another interesting application is for acoustic detection in bubble chambers. Bubble chamber is a chamber filled with a superheated liquid like C3F8, and it's when a particle goes through, it deposits a little bit of energy, and that nucleates a bubble, which can give an optical signature, but also an acoustic signature. And this is currently being used to search for dark matter, for example, the PICO collaboration, and at SNOLAB in Ontario, Canada. And we're in discussions with them about possibly using our methods for acoustic detection in a bubble chamber. And so if successful, this would be quantum limited detection of sound generated by one of these events. So I think it's interesting applications which kind of come out of fundamental measurements of short-time Brownian motion. And then finally, just to update on the Pointsman Foundation. This is a nonprofit foundation that grew out of our work and is now being developed quite a bit since last few years. The current projects are isotopes for medicine, public health, and fundamental physics, and you can read about them at the website www.pointsman.org/projects. We also have created a new structure for this operation, where we have the Pointsman Foundation, which is a nonprofit entity, and it is 100% owner of the Pointsman Lab Inc. And the Pointsman Lab Inc. then is a majority owner in companies that it generates. Our first successful company, Atom Minds LLC, is now producing a key isotope for cancer therapy. So this is we are pursuing, and will allow us to do many projects that don't have a business model, just benefit to humanity. And finally, one of the things we can do at the foundation level is we can produce radioisotopes for atom aging experiments. So this kind of closes the circle. In fact, we are set up to produce lutetium-177 from ytterbium-176 or lutetium-176. We can produce strontium-89 from stable strontium-88, and then do post-irradiation separation in a hot cell. And so we are well positioned to provide these short-lived isotopes for testing quantum mechanics. I will end here and thank you for your attention.